going to talk about random matrices from Painlevé to KPZ.
Yeah, so thanks a lot, Milton. Thanks a lot for all of you for being here and also there at IMPA or wherever you are. So it's one of the things that we learned from pandemics that we can now share things a little bit more easy. I mean, a little bit easier. I mean, I'm very glad to be here. Okay, yes, I want to talk about random matrices and some connections that we found like recently. Okay, but let me get started. Actually, I was mentioned that actually there are many students, so I thought that would be a good idea to spend some decent amount of time talking about some basics in random matrix theory. Okay, so what's a random matrix? Well, it's a matrix with random entries, and you can choose to define this matrix in your favored way. For us, we'll be dealing with Hermitian matrices, right? And of size n, capital N here. And moreover, we will impose that those matrices have a sort of a joint distribution, right? And this joint distribution takes the form of a, so to speak, Gibbs measure, right? So you look at your matrix M as, let's say, like a bunch of random variables. The entries are random variables. The matrix can be complex, so we just look at real and imaginary parts as random variables. And this lives in a high-dimensional Euclidean space. And then you just impose in this Euclidean space like this Gibbs measure, where here, let me read what everything is. So dm here is just a Lebesgue measure on this high-dimensional Euclidean space. Here you have v of m. So v for us, it suffices to assume that's a polynomial. So take trace of v of m. Since my matrix, the matrices are assumed to be Hermitian, trace of v of m gives a real number, and then you multiply it by n. It's convenient for normalization reasons. Okay, then exponentiate, and this becomes essentially a function, a real valued function, a non-negative function. And you see it as a measure, right? You have to normalize it and also ensure that that the total integral of this guy here is actually finite. But anyway, you can make sense of that, and this becomes just like a sort of a Gibbs measure and defines a probability measure on the space of matrices. Okay, first things first, the most concrete case you could think of. Imagine now that you take your v to be a quadratic polynomial, let's say x squared or proportional to x squared. Then what you learn in this case is that actually you don't have to talk about the Gibbs measure. In this case, you can actually express everything in terms of the individual distributions of the entries of the matrix itself. And in this case, the entries are just Gaussian random variables. And they are independent. And by here independent, I mean modulo the symmetry. We're talking about Hermitian matrices, so you know that m equals m star. So you cannot talk about, you cannot say that all the entries of your matrix are independent, but you just look at, let's say, the diagonal part of your matrix and the upper triangular part of your matrix. All the entries over there, they are pairwise independent. And yeah, because then like the lower triangular part of our matrix, of course, is then completely determined by just the symmetry they're imposing your matrix to be Hermitian, right? And this is what we call the Gaussian entire ensemble. Again, why Gaussian? Just because the matrix, the entries of your matrix are all Gaussians, complex Gaussians, they are independent. And here the unitary just comes from a certain symmetry, because your matrix is Hermitian, and this model is essentially invariant under unitary conjugation. So that's why you add this unitary part here, right? Okay, yeah. So in other words, a very concrete case. If you don't care about Gibbs measures, a very concrete case is when you take v polynomial, a quadratic polynomial, and then essentially you're talking about Hermitian matrices with Gaussian independent entries, right? Okay, okie dokie. And what can you do with that? Well, first of all, your matrix is Hermitian, which means that the eigenvalues are all real, right? So we learned from linear algebra that the Hermitian matrices are diagonalizable. So if the matrix is random, you get actually also, again, eigenvalues, but they are random, right? And real in this case. And we are mostly interested actually in real eigenvalues, right? what actually are the kind of the classical questions that one wants to ask about eigenvalues, or that people have been asking the past 30 or so years, or even more so, about eigenvalues. So there are several sort of aspects that are interesting in random matrix theory. The first one of them is that you have exact solvability. So random matrices provide a good sort of a good background to make predictions in physics and to describe, let's say, new phenomena. And in our concrete case, in this class of matrix models that we are talking about, you can see this exact solvability, for instance, at the level of eigenvalues. So as I said, you start Hermitian matrices, this kind of Gibbs measure, eigenvalues are random, real but random, but actually you can actually write down explicitly the joint distribution of eigenvalues. So if you look at these eigenvalues on, let's say, as let's say n components of a vector in Rn, then you can view this vector, of course, as a random vector, and the joint distribution of this random vector is the one that you see here on the screen. So it still has this product here of v of minus n v lambda k, which is just reminiscent of the Gibbs form or that you started with at this space of matrices. But you also have another factor here, which is, for those who recognize, a van der Monde determinant squared. So if you forget about this factor here, you would think that the eigenvalues are just independent random variables with kind of an exponential type distribution. But you do have this this factor here, this van der Monde square, which gives local interactions between the eigenvalues. So they are strongly correlated, and actually the correlation decays the correlation decays the square of the distance, or goes to the square of the distance, right? So in a certain sense, so that means that the eigenvalues are correlated, and they actually have a certain repulsive behavior. The closer two eigenvalues get to one another, the smaller the probability of finding this event, right? Because of this van der Monde effect, right? So yeah, and this essentially you can view directly just because you have exact solvability. So a very, very explicit form. Okay, and what do you do with that? Okay, you could start asking questions more, refined questions about eigenvalues. But in practice, we're interested in eigenvalues of very large random matrices. So when n grows to infinity, the size of the matrix, so you have more and more eigenvalues. And in this case, if you look at this distribution, this is a distribution Rn, and let's say n is growing, so sort of varying space. So this exact formula here is not exactly useful for asymptotics, but you can still work your way through. And one of the consequences, or another form of solvability of the eigenvalues, is what we call the determinantal form. So if you look at this distribution of eigenvalues, it admits another expression. It's just an algebra, just like some algebra that you do here on the right-hand side, and you can express this as a certain determinant. So here you have, so what am I doing? Instead of looking at this as a function of n variables, essentially I'm encoding everything in terms of a function of two variables, which I'm calling here kn of v. I won't write it explicitly, but it's rather explicit here. I'll just make some comments later. But the core information I want to tell you about is that essentially what you're doing is that you're decoding everything on your eigenvalues in this function of two variables, with the caveat that actually you still have to handle a determinant of size n by n. Okay? But anyway, everything now boils down to a function of two variables. And the fact that you can write down this joint distribution, this determinantal form, expressing everything in terms of a function of two variables, is what we say that the eigenvalues are actually a determinantal point process. So what does it mean, like in more general terms? Imagine that you have a certain particle system, let's say on the real line, for the sake of concreteness. And so you have certain random points, lambda j, and we say that those random points form a determinantal point process if you can find a function of two variables, k, for which this kind of generating function, so you take like products of 1 minus phi of lambda j, so take some sort of very general family of expectations. Here phi is just like some sort of regular enough test function, and the point, this point process determinant, those expectations, they can be expressed in what we call a Fredholm determinant. It's a series, but don't care much about it, about the exact form of it. The most important part is that everything here, all those multiplicative statistics, they can be computed solely in terms of a function of two variables. So in a sense, everything that you want to say about your point process is encoded in this function of two variables. In the sense that all statistics, or let's say a very large class of statistics of your point processes, can be computed in terms of this Fredholm determinant generated by this kernel, which is called the correlation kernel, right? Again, don't care much today about the exact form of these expressions. A little bit cumbersome, but the heart of the matter is that the terminal point processes are nothing but point processes for which their statistics are encoded in a function of two variables, right? Just some like extra comments, which are not very important for today, but anyway, let me mention that. The first thing is that if you consider like a large family of test functions phi, essentially those statistics, they generate your point process. They uniquely define your point process. So in a certain sense, the kernel K also uniquely define your point process. And the second comment also that I want to make is that this determinant here, although I'm just defining it as a series expansion, it also has an interpretation in function analysis. This is what's called a Fredholm determinant of the integral operator determined by the kernel K, right? And that's particularly relevant when you want to do asymptotic analysis, because you can use function analysis or tools from function analysis to do so. Anyway, again, just have in mind that determinant point processes are point processes which are essentially encoded in a function of two variables. And for us, yeah, as I just said, and for us, most important, eigenvalues also form a point process. So everything that you may want to say about eigenvalues of random matrices is encoded in this function of two variables, and that's pretty nice. Essentially, now all you want to do is, if you want to, let's say, study asymptotics for any quantity that you're interested in, for random eigenvalues, the first thing that you have to do is to understand how the behavior of this kernel, let's say, when the matrix grows, right? And for this family here of these measures, this kernel here is explicit and is explicitly given in terms of orthogonal polynomials for this measure here, exponential minus nv, right? Okay, okie dokie. So this sort of exact form integrability. Everything they want to ask may be answered if you just understand this function of two variables, essentially. Okay, and for instance, what kind of questions people have been asking and answering, studying this kernel? The first thing that one nature question that arises is concerning the behavior of eigenvalues. So you could say that you consider here what we call the counting measure for eigenvalues, or the density of states, right? For the point process. So you just consider here that some point masses at each eigenvalue, which is random, we divide by 1/n, so that this is really like a probability measure. And it's a random probability measure that encodes your eigenvalues, the position of eigenvalues. And what one can prove, essentially exploring these interpretations of the determinant point process, is that this random measure converges to a deterministic measure, which I'm denoting here mu of v. Okay, the measure is random, so take it as almost surely convergence in an appropriate sense. Yeah, and what I have to tell is what this mu of v is. But this is what the people call equilibrium measure. In a certain sense, this statement here is law of large numbers for the eigenvalues, right? So just saying that eigenvalues converge to the equilibrium measure with respect to the potential v. And this equilibrium measure is actually can be found using a variational problem that I'm going to state in a moment. But let me just give you an example concretely. So imagine now that you started with like this Gibbs measure with a potential v, which is quadratic plus quartic. What I'm doing here is I'm introducing here a parameter t as well, in the quadratic part of your quartic potential. And what I'm depicting here for you in blue is the density of the equilibrium measure when t is exactly 0. So when t is exactly 0, you have this density here, which is almost like a semicircle, but not quite. And what it means that if you read it off, it means that eigenvalues are with very high probability when n grows inside this interval here where the density is positive. And if you are in a certain small interval here, the probability of the average number of eigenvalues that you'll find in a small interval here corresponds to the height of this function here in the interval, essentially. Anyway, and this is the equilibrium measure that you see for t equals 0. And now, so you fix t, you take n to infinity, you find the corresponding equilibrium measure for t equals 0. This is the density of this equilibrium measure. And now let me just start tuning up t. So when t goes from 0 to -3, of course, the smaller the t becomes, you start to move to change this density of this equilibrium measure, and you change it up to the point that, okay, it starts to, in the middle, close to the origin, the equilibrium measure starts to decay as a function of t. And at some point, we even get to the point where the density exactly at the origin becomes 0, and then actually splits into two intervals. So what we're saying here is that now eigenvalues for t equals -3, for instance, the larger limit, eigenvalues accumulate almost surely in this interval here, on the negative axis, and in this interval here. Right? And probability of finding eigenvalues in another interval, disjoint from those two, actually decays exponentially to 0 with n. Anyway, so this is a picture of the equilibrium measure. And how do we actually compute it for this v and for general v? So this equilibrium measure satisfies a variational problem, which is the following. You start, again, with this potential v, and then you search for a certain probability measure on the real axis, which minimizes this functional here. So what do you have here in this functional? You have a certain external field acting on your measure, which is driven by this v, right? And you also have certain inner interactions. So if you play around, what you're going to see is that if you're trying to minimize this functional, you're going to see that this term here, this logarithm term, gives some certain inner repulsion in the density of your minimizer. And this term here gives some repulsion from infinity on your minimizer. Okay, you do some potential theory, and then what you learn is that there is a unique minimum for this functional. If v is regular enough, there is a unique minimum for this functional, overall probability measure on the real line. And this unique minimum is what we call the equilibrium measure. With a little bit more work, you show that actually this equilibrium measure really describes the limiting eigenvalue distribution in the limit of large matrices, right? Okay, that's nice. There's a variational formulation for that. And you can also study qualitative properties or more quantitative properties, better to say, of this equilibrium measure. And the picture showed to you for t equals 0, the density of this equilibrium measure was actually supported in a single interval. And when t was starting to be negative, and for instance, when t was -3, the density was supported in two intervals that you see here. And in general, for any polynomial potential v, you actually can prove that the density of this equilibrium measure is actually compactly supported, and the support consists of finitely many intervals, finitely many intervals, and actually the density itself vanishes as a power of a square root here at the endpoints. So in other words, you have some quite refined control of the global density of eigenvalues in the large matrix limit. Okay, so far so good. And as I told you, one way to prove those results is pretty much because you know the eigenvalues from the determinantal point process. So essentially you can translate everything, all those statements here, into statements about the limiting behavior of the correlation kernel that I showed to you in the previous, some minutes ago. Okay, good. So once you grab a thorough understanding of eigenvalues, let's say in a global scale, all eigenvalues are knowns, you may start asking about more refined questions. Let's say, let's say the law of large numbers for eigenvalues. You can ask also about, let's say, central limit theorems for eigenvalues, so fluctuations. And for instance, what the result I just told you about the law of large numbers give you, for instance, is that if you take, let's say, the maximal eigenvalue, then by just exploring the result I told you before, you know that the maximal eigenvalue will converge to essentially a very well-defined limit, which is essentially, for the maximal eigenvalue, is going to be the rightmost endpoint of the support of the equilibrium measure. Here I'm just doing it just like then, and you can start centering around this limiting point. Let's say I'm centering around its average, right? Then start looking at fluctuations, let's say of the maximal eigenvalue here, right? Okay, under certain conditions, I don't want to talk much about that, but certain very mild conditions on the equilibrium measure, you can actually prove that the fluctuations of the, let's say, largest eigenvalue are of order n to the power 2/3, or 1/n to the power 2/3, and here should be really a minus 2/3. And then when you scale things correctly, and this should be a minus 2/3, you actually can prove a central limit theorem for, let's say, the largest eigenvalue. And the fluctuation of the largest eigenvalue, appropriately scaled, are given by the Tracy-Widom distribution. So in other words, now that we are talking about eigenvalues, the corresponding central limit theorem is no longer given by a Gaussian for the maximum eigenvalue, but it's given by another distribution, which is the celebrated Tracy-Widom distribution. I'm going to tell you what it is in a moment. And you should really appreciate this result. And this result is one perhaps of the first instances, or one of the most classical instances, where you see a model where you have, when you have strong correlation between random variables, and then the corresponding central limit theorem for some extreme statistics fall very much far away from the usual central limit theorems for independent random variables. So you don't see Gaussian here. We don't see like Gumbel or those others, other limiting distributions for extreme statistics, but we see a very different one, which is the Tracy-Widom distribution. And this has a lot to do with the strong correlation between eigenvalues. Because you're talking about, let's say, a maximal eigenvalue, and the maximal eigenvalue is the maximal of a set of very strongly correlated random variables. Remember that when I told you, like if I showed to you like some of the exact forms for the distribution of eigenvalues, there was this van der Monde determinant, which was telling us that eigenvalues have a repulsive behavior. So they are strongly correlated. And the correlation is so that actually when you look at fluctuations, the correlation still plays a major effect. And for instance, you break down the usual central limit theorems, and for the maximal eigenvalue, what you get is the convergence to the so-called Tracy-Widom distribution. Yeah, and what I have to tell you now is what this Tracy-Widom distribution is. Okay, but before saying that, let me just make a few comments what I mean by the square root type behavior, right? So again, this square root type behavior is what determines the order of correlations here, which should be n to the power minus 2/3. And as I told you, the square root behavior has to do with the behavior of the equilibrium measure. And what am I talking about is the following. This kind of central limit theorem works, for instance, when you look at, let's say, fluctuations around this point here of the equilibrium measure, which is not a maximal, an extremal point. It's not like, it doesn't correspond to the maximal eigenvalue, but corresponds to extremal eigenvalue, doesn't matter. And the density of the equilibrium measure in this point vanishes as a square root. So in this case, this central limit theorem holds true if we scale things around this point here. Also in this case, which then corresponds really to the maximal eigenvalue, but not quite in this case. Why not? Because this is not really an extremum in the statistics in the sense of a local extremum. Why? Because you see that the density of eigenvalues here is positive both to the right, to the left, and to the right. So you have like close to the origin, you have eigenvalues on both sides. So this is what we call a bulk point. And those are like edge points, really extremal points, true extremal points for the eigenvalues. Yeah, and this result here, as I told you, is really a universal result, that in the sense that whenever you have a certain extremal statistic for eigenvalues in this Hermitian matrix model, and the density of eigenvalues vanishes as a square root, which is a generic case in topological sense, then you have the corresponding central limit theorem for the fluctuations of extremal eigenvalue has as a limit the Tracy-Widom distribution. Yep.
I have a question. In the first picture,
yes,
how do you
yes,
define
sure.
do you define the lambda that you wish to observe the fluctuation?
You can essentially order here the eigenvalues, and you see. I mean, in this case, symmetric, so you know that half of eigenvalues will be here, half of the eigenvalues will be here. So just take the half in the middle, right? But in general,
Is it true that exactly one half will be on one side and exactly a half on the other side?
It's not exactly, but up to exponential is you have to make sense of that in probabilistic terms. But you know that there is exponentially small number of eigenvalues which will be outside those two intervals. Let me be a bit more precise. You fix, let's say, a small tolerance. So instead of looking, well, let me call this interval minus 2, 2. It's not exactly minus 1, minus 1. Minus 2, minus 1. It's not exactly this interval, but no, almost, right? So what you do, you make a small tolerance here, small tolerance here. So you just put a slightly bigger set, which contains this interval, and that contains this interval as well, right? And then what you prove is that for this slightly enlarged set, the probability that you find eigenvalues outside this set decays exponentially small. And then let's say that you want to look at extremal statistics here. Then what you do, you fix a small interval here, which contains this interval here of positive density. And then you look at the smallest eigenvalue, which falls inside this interval. And then you look at fluctuations of the smallest eigenvalue that falls inside this interval here. Then you prove fluctuations for this eigenvalue.
Okay, and coming back to this symmetry argument, what is there a known result concerning the fluctuation of the fluctuation around n/2 of the number of eigenvalues that you have on the left?
Can you say it again?
So you told me that the separation, the eigenvalues are not exactly one half in one interval and one half in the other.
Yeah.
That you can have some fluctuation. Do you know the order of this fluctuation, or
of the ones that are outside? I guess you do, but I don't know by heart.
Okay.
Essentially, what you can capture is that because you have two intervals, essentially you can, if I remember correctly, you can have at most one for each n. When n grows, you have at most one eigenvalue which is not in those two intervals, or which falls away from those two intervals, except for exponentially small corrections.
Mm-hmm.
In other words, really just one eigenvalue which will not be in those two, except for exponentially small corrections. Exponentially small, I mean n.
Okay, well, thank you.
Yeah. Okay, so this is sort of a central limit theorem, like universality result for eigenvalues, for extremal eigenvalues in a very generic case. And let me tell you what this Tracy-Widom distribution is. And that's okay. And this is, as I told you, so this central limit theorem concerns those two situations here, not this situation. Okay, let me tell what this guy here, F2, is. Historically, it was actually given, it was found more or less at the same time by two different groups. The first group was Tracy-Widom, and due to their results that we call this distribution the Tracy-Widom distribution. And what they found is that in the Dewey model, the one where the entries are Gaussian random variables, this F2 can be constructed or is completely characterized in terms of a certain differential equation. So if you take the second log derivative of this F2, this is a perfect square, or minus a perfect square, where this term Q here is a specific solution of a certain differential equation, which is what we call the second Painlevé differential equation. So this is a nonlinear equation of second order, and there's a whole theory about it. And if you impose a certain asymptotic behavior at plus infinity, there's a unique solution, and this unique solution essentially reconstructs your Tracy-Widom distribution. Right? And I'm saying here F2, this 2 here has to do with the repulsive behavior that I told you that the eigenvalues are, they have this repulsive behavior proportional to the square of the distance between consecutive eigenvalues. The 2 here is precisely the square over there. There's a whole family if you put a beta there, but for another day. Right? Yes, in other words, Tracy, we don't characterize, they prove that there is a limiting distribution. They prove the central limit theorem for Gaussian unitary matrices, and they characterize the central limit theorem in terms of the distribution in this central limit theorem in terms of the second Painlevé equation. About the same time, Peter Forster also found another characterization. At that point, they were communicating. Peter Forster didn't compute the central limit theorem itself, but worked directly with the limit. And what he proved, or at least he didn't prove the central limit theorem rigorously, just formally. And then he studied the limit itself, and he characterized this limit as a Fredholm determinant of a very specific, let's say, function of two variables, this correlation kernel, which is what we call airy kernel. Again, it's a function of two variables, which depends on t here. On this t here should be s. T and s here are the same thing. So this function of two variables depends on this on s, on this parameter s here. When you take this Fredholm determinant, you get a function of s, which gives then this Tracy-Widom distribution, right? And this function of two variables is constructed precisely in terms of airy functions here in the middle, a certain convolution of airy functions. So two different characterizations of the same object, right? As I told you, in both of those works, they were working with Gaussian unitary matrices, so matrices with Gaussian entries, but we know many years later, actually, we got to know that the central limit theorem that I just showed to you, where the limiting distribution is given by the Tracy-Widom distribution, was proven like under various different assumptions by like various different groups. Yeah, and one comment I want to make is that remember that in a few slides ago, I told you about this determinantal point processes. And essentially, this kernel here defines also the determinantal point process, which is what we call the airy two-point process. And this limiting distribution Tracy-Widom is precisely the limiting distribution for the largest particle in this airy two-point process. Right? So the reason it appears, this airy two-point process, sort of can view like not only a fluctuation of the largest particle, but fluctuations of all the particles, the right scaling. Essentially, eigenvalues are converging to this airy two-point process. And so when you specify the largest eigenvalue, what you're doing is that you see in the limit precisely the distribution of the largest particle in this airy two-point process. Okay. So this is what I wanted to tell you, like in terms of eigenvalues of random matrices, which took me a little longer than I was planning, but okay. And what I want to tell you about today, or mention a little bit more, is about the deformation of what the picture showed you before. What they're doing here, so I want to look at not exactly eigenvalues, but certain particular statistics of eigenvalues. So before, let's say, I talked a lot about the largest eigenvalue, or the distribution of the largest eigenvalue, central limit theorem for the largest eigenvalue in the random matrix model. But now I want to look at another quantity, which is not only like the largest eigenvalue, but another statistics, which is actually this kind of multiplicative statistics. So here for me, I mean, the reason I'm doing this specific statistics is motivated by several, by other words and by other reasons that will comment along the way. For now, just take it as I'm taking a function Q here, which is, let's say, will be later specified, let's say, or better to say, later I'll give some more conditions on Q, but for now, let's just assume that Q is a very sufficiently regular function, and then it means I'm just looking at multiplicative statistics indexed by this function Q, so treat it as a test function. I'm doing certain scalings here, which have to do with the scaling of the largest eigenvalue, but don't bother about it right now. I'll explain those scalings later. The core of the fact is really that I'm looking at certain multiplicative statistics rescaled in an appropriate way. And if you complete the multiplicative statistics, because we have this explicit solvability of eigenvalues, the multiplicative statistics can be computed exactly, sort of a n-fold integral that you see here on the right-hand side. And if you just focus on this part here and this exponential part, those two terms combined, they correspond just to the joint eigenvalue distribution of the original matrix model, but now we just add this term sigma here, which is the one that corresponds to computing the statistics themselves, right? So the sigma here is just the symbol of the multiplicative statistics, right? This is a quantity that we're going to be looking at. And again, this quantity is indexed by a certain parameter S. I'll tell you in a moment what that is. Just treat it as a parameter. In other words, we are doing certain general multiplicative statistics in a certain scaling and indexed by a certain parameter S. And I'll tell you by the end of this slide why we care about those. And there's another thing that I want to connect this thing to a certain limit object. So the theorem that I want to tell you in a moment is what the large n behavior of this Ln of Q is when n grows. And so I have to tell you what the limiting counterpart is. And this limiting counterpart is going to be a function of two variables, capital S and capital T. It's going to be indexed, it's going to be a Fredholm determinant indexed by a function of S and T, which you see here. And what is this Fredholm determinant? Again, it's a series that's constructed out of a function of two variables, A, and this function of two variables, which also depends parametrically on S and T, takes a form which is almost like the one that you saw on the previous slide, but on the previous slide, I had, instead of the sigma, what I had was a characteristic function, dy in this case, right? Yeah, so this one here. Right? So in the previous slide, when I talked about the Tracy-Widom distribution, the Tracy-Widom distribution is the limiting, is precisely this L of area when I replace sigma by a certain characteristic function. Right? And now I'm extending this to a more general symbol function. And what I plan to do is to convince you why we care about this kind of quantity. Right? Okay. Yeah, and just to say this kind of Fredholm determinant, again, it's like a certain multiplicative statistics of certain process, and this is essentially multiplicative statistics of this area 2-point process. Okay, and this is the theorem that I want to explain to you, or better to say, I want to explain to you in the next slides why we care and why it's interesting. So what is the theorem? So again, so we look at these multiplicative statistics for the random matrix model. And then also, once you do the proper scaling, these multiplicative statistics of the eigenvalues converges to this certain function of two variables, S and T. S and T, they are just scalings of this small s and of the first derivative of Q. So the first thing that you will note is that the right-hand side here doesn't quite depend on Q except for its first derivative. So this result here is universal, first of all. And second, this right-hand side here is a multiplicative statistics of certain very particular point process, which is the area 2-point process, right? So this theorem is just saying that appropriate scaling of multiplicative statistics of eigenvalues converges to multiplicative statistics of this area 2-point process. I'll give a more precise version of this result if I get to that point. But really, the take-home message for today is we have a certain new universal result saying that a very general class of multiplicative statistics of eigenvalues converges to a limiting object, which is a multiplicative statistics of their two-point process. In the next few slides, I want to explain to you how this limiting object connects to the KPZ equation and a certain extension of this Painlevé 2 equation. And that's why we care about this limiting object. Yeah. So this object here that I just showing to you, this limiting object, we are not the first ones to see it appearing. There's a work of Kurt Johansson from 2007 where he considers a very specific matrix model, and this guy here pops out all of a sudden in a certain appropriate limit, right? And a few years later, it was realized that actually this limiting guy is essentially a Laplace transform of the narrow edge solution to the KPZ equation. So you take the solution to the KPZ equation, which is a stochastic equation, you rescale it appropriately, and you have certain variances. So, okay, you scale it and look at the origin, which you can do without loss of generality. And after you do this scaling, so you introduce a certain parameter S, which you should view it more or less as sort of a spectral parameter or some sort of Laplace transform parameter of your solution to the KPZ equation. And once you do that, you take expectation with respect to the KPZ equation itself, spatial expectation. Expectation by the KPZ equation, right? You solve with an expectation of this guy here. And there's a certain scaling here. So T here is time in the KPZ equation. So capital S here is a spectral variable in the KPZ solution. T here is time in the KPZ solution. Then take this sort of Laplace transform. And what was realized by two groups of people actually is that this expectation, the KPZ side, this Laplace transform, the KPZ solution, course, is exactly coincides exactly with this multiplicative statistics of the every two-point process, right? So this was realized by first somehow in an implicit way by Amir Cohen Quastel. In a work where they actually find the distribution, exact distribution, one-point distribution of the narrow edge solution to the KPZ equation. So they solve exactly the KPZ equation in a sense, and this identity here was the key identity there, because once we have this identity here, you can sort of invert this Laplace transform and obtain actually distribution of the KPZ equation itself. Right? But at that point, they didn't really realize that the identity that they had over there was coinciding with like the multiplicative statistics of their two-point process. But almost soon later, they really realized that, and this was written down explicitly actually in a very short paper by Alexei Borodin and Vadim Gorin in 2016. Right? In other words, they had this identity. Amir Cohen and Quastel did have this identity. They just didn't realize that it corresponded to a certain quantity in the air two-point process, and those two guys, they did realize and wrote it down, right? Yeah. So in other words, what we're seeing here is that a certain quantity that the Laplace transform of the KPZ of the solution of the KPZ equation coincides with the air two-point process and describes also some limiting statistics of eigenvalues of random matrices, right? And also in this work of Amir Cohen and Quastel, there was a certain formulation saying that this multiplicative statistics, you take its second log derivative, and it can be written as in terms of a certain term, which solves what's called the integral differential Painlevé 2 equation. Again, don't care about the details. What's important here is the original trace width distribution solves the Painlevé 2 equation, and this multiplicative statistics solves a non-local version of this Painlevé 2 equation. So in a certain sense, this characterization of this multiplicative statistics here is an extension of the original trace width result and connects to differential equations, right? In other words, if you want to describe this Laplace transform the KPZ equation, you may want to solve, one possible way is to solve a certain local differential equation, which is an extension of the Painlevé equation. There are several works that I should mention here, especially recently, and this kind of identity, especially this trace-Widom type formula, has been found in various different works. So either this quantity that you see here, or related quantities in random matrices or other point processes have been found to be some sort of universal in other models as well. Many recent works here. And in particular, perhaps I should mention here that this identity here was in particular very, very powerful for studying the tail behavior of the fluctuations of the KPZ solution in a large time limit. And for instance, exploring this identity, already in the works of Amerkor and Costel, there was a proof that in the large time limit, the KPZ solution converges to the trace-Widom distribution, or the one-point distribution of the KPZ solution converges to the trace-Widom distribution. More recently, people, Corin and Gusau especially, they also used this identity to get some tail behavior for the narrow-edge solution of the KPZ equation, again, in the large time limit. And why? Just because you can translate your question, the KPZ word, to a question concerning statistics of point processes. And because you have exact solvability for point processes, you have lots of tools to explore, tools that are also inspired or learned from random matrix theory, right? So this identity is quite interesting, so to speak, and quite powerful. Yeah, okay, but let me put this result in a more general framework, or our result in a more general framework. What exactly is the KPZ? I'm assuming that many of you have been seeing have worked or heard about KPZ universality or KPZ equation. The picture or the video that I'm showing to you here is an animation of TASAP or ASAP, actually. And what you see here, ASAP, okay, like a symmetric simple exclusion process, that you see the points here on the real line. I'm capturing here a height function. If you know what it is, you know what it is. If you don't know, I won't give you much details, but just have in mind that this is like you have a certain point process here, correlated points on the real axis, and they evolve in time according to exclusion rules. And you can encode that into a height function, which is the blue function here, which is a random function, right? Points move here on the real axis means that this height function moves upwards, right? And the green function that you see here is essentially the expected value of the blue function, right? So the blue is a stochastic growth model, and the green is its average, right? And the stochastic growth model is coming from exclusion process, right? There are certain parameters there, and if you tune up your parameters appropriately, what you actually get is that this blue curve here essentially corresponds to the solution to the KPZ equation, right? Yeah, and what the KPZ universality is about is actually that there's a large family of growth processes which should all have in the large time limit the same limiting statistics. In other words, there's a certain central limit theorem which is common in the appropriate scaling to a very large class of growth models, 1 plus 1 dimensional growth models. You can view that in several ways. One way to view that is by looking at, let's say, 1-point distribution. So you take your growth model, let the time grow, and then look at 1-point distribution, the very large time for a growth model, and the fluctuations of this growth process, the 1-point distribution for the fluctuations converges to the trace-Widom distribution. This is one form of KPZ universality, right? And as I told you, as I mentioned to you, essentially this result of Amerkor and Costel is saying that the KPZ equation belongs to the KPZ universality class, in the sense that the 1-point distribution of the KPZ equation in the large time limit after appropriate scaling converges to the trace-Widom distribution. Another result, which is, I guess, the first time that I can tell, that I remember was given by Tracy Williams as well in 2007, 2008, is concerning the ASAP. ASAP is a certain scaling here of this particle system, or it's precisely this particle system that you see here in the video. It turns out that if you let time grow in the appropriate scaling, the ASAP converges to the Tracy-Williams distribution. 1-point fluctuations of the ASAP converge to the Tracy-Williams distribution. And the result that I told at the very beginning for the largest eigenvalue of random matrix is essentially reminiscent of that. The eigenvalues of random matrices at properly scaled converge to the Tracy-Williams distribution, so they belong in a certain sense to the KPZ universality class. Right? But there are also other sort of limits that you can take from the ASAP. For instance, there's a limit that you can take, not letting time grow, but then not only let time grow, but also scaling certain parameters, which is what we call the ASAP limit. And there's a way to see that ASAP converges to the KPZ equation, right, in appropriate scaling limit. And there's also another limit, sort of opposite, that you can see that the particles of the ASAP converge also to eigenvalues of random matrices, right? So you can sort of commute diagrams here, right? Those words I'm talking here about the late 2000s or early 2010s, those results here. And essentially what our result, the one that I mentioned to you, if Ramit Gusau is saying, is that you can actually also take, in a certain sense, a limit of eigenvalues of random matrices, and in a certain sense, capture statistics for the KPZ equation. Right? So that's essentially our result. Right? In the sense that certain multiplicative statistics of eigenvalues of random matrices converge to the Laplace transform of the narrow-edge solution to the KPZ equation. Yep. Okay. So far, so good. How long do I still have?
A few minutes.
Few minutes? Okay. So what I told you before, so I gave you a glimpse of our results saying that certain multiplicative statistics of eigenvalues of random matrices converge to this multiplicative statistics of the RH 2-point process. But I didn't give you like a very precise result in the sense of conditions. So I just want to go very briefly over the conditions over there for that theorem to hold. Again, just to remind you what I did, I look at the multiplicative statistics of this guy here, right? So just to have in mind, so this S here is just a parameter. I'm doing a certain scaling here of N, which is the size of a random matrix, and Q is a sufficiently regular function. And now I'm going to just place conditions on Q and on our model. Okay, yeah, on this base, essentially the density is integrating here. It turns out that if after a proper scale this guy here, essentially this guy is also, the statistics can be written in terms of the determinantal point process as well, the determinantal form, and that's essentially the first thing that we actually use it. Okay, let's not bother much about that. But what I do want to say, though, and perhaps in the very last slide I'll make comments about, is that essentially you can interpret this kind of multiplicative statistics as being a certain conditional point process. So if you just renormalize things, you can generate a certain conditional point process on the eigenvalues, which correspond essentially to removing eigenvalues with certain probabilities and then making a further conditioning. And this kind of statistics essentially capturing this conditional point process. The core of the matter is that then you can essentially write down these multiplicative statistics in terms of a certain kernel here. Again, I will not bother much about the specifics, but just all of this just to say that these statistics can be computed explicitly in terms of a certain kernel here, where this pk of Q is an orthogonal polynomial with respect to a deformed measure indexed by Q. Okay, technical, but now finally to the things that I want to talk about. The previous slide I told you is just to say that this kind of guy, so this Q here, this indexing my statistics, should be viewed as a deformation of the original matrix model. So I start with a matrix model with a certain potential V, and the Q induces a certain deformation on this matrix model. And technical reasons, what we're going to assume about the original matrix model V, the matrix model that we're computing statistics of. So the original matrix model depends on a certain potential V. There is a certain equilibrium measure that I told you in the very first slides, and we assume that this equilibrium measure is supporting one single interval. Just technical condition. I mentioned to you they could have various components of the support, but just for technical reasons, we assume, just for simplicity, that the equilibrium measure itself is supporting a single interval. Moreover, that the density of this equilibrium measure vanishes as square root. In other words, that the fluctuation of the largest eigenvalue are given by Tracy-Williams distribution. Generic assumption. And most important, we assume that this Q, which is kind of playing the role of a deformation of our matrix model, satisfies certain conditions. First of all, it's analytic on the neighborhood of the real axis. Second, we assume that this Q is strictly positive on the negative axis and strictly negative on the positive axis. What does really mean is the following. So we view this guy here, the statistics, as a certain deformation of the original matrix model. And when n grows, those conditions on Q, what they're saying essentially is that on the support of the equilibrium measure, this deformation is almost like 1. And to the right of the support of the equilibrium measure, this deformation is almost like 0 when n grows. N is the Euler matrix, right? In other words, the equilibrium measure here describes the eigenvalues. So in the larger limit, the eigenvalues are mostly in this interval here, minus a to 0. And what we're saying here is that our deformation doesn't change eigenvalues drastically. Why? Because the deformation is essentially 1, where the eigenvalues live in the limit, and it's 0 outside where the eigenvalues do not live. But it turns out that there are corrections, because this function here is an approximation to so this deformation here is an approximation to a characteristic function. But there are corrections which happen exactly at the scale, close to the origin here. The origin is where the largest eigenvalue lives. And actually, we impose that Q vanishes linearly here at the origin. And the fact that it vanishes linearly imposes a certain scaling here on n. And this scaling just has to do with the scaling of the largest eigenvalue. So I told you before, the largest eigenvalue, the fluctuation of the largest eigenvalue in this under our assumptions, they will be of the order 1 over n 2/3. And then I'm just scaling, putting the scaling up front exactly to perturb the fluctuations at the critical scaling. In other words, this n 2/3 here has to do with the scaling, the critical scaling of eigenvalues of the largest eigenvalue near its expected position, right? All of this just to say that what we impose in our deformation here, in our Q, is just that Q is essentially a perturbation of a characteristic function, and a perturbation for which non-trivial terms or non-trivial corrections happen exactly at the same scaling as the fluctuations of eigenvalues, so that we are perturbing the fluctuation of the largest eigenvalue in a critical manner, so that we don't see anymore the original central limit theorem for Tracy-Williams distribution, but that we see something non-trivial or something different, right? And the other thing that I want to remind you is that this S pi meter is just a pi meter for us that survives, a spectral pi meter. And there's another pi meter that I want to call your attention to, which is this pi meter T, which is the first derivative of Q. And this T here, I want to highlight it just because the only thing that survives from Q. So you start with any function, sufficiently regular function Q here satisfies certain conditions, and essentially everything that will survive in the limit for this limiting critical quantity is precisely the first derivative of Q, right? Which has to do with the time in the KPZ equation. That's why I want to keep it, right? Okay, so those are technical conditions. And just to remind you, there was this limiting statistics, and we are assuming also a certain regular behavior of the equilibrium measure. And here's the theorem that I showed you at the very beginning. And so the theorem more precise is the following. You take the multiplicative statistics of your eigenvalues under those conditions, You do a critical scaling, forget about this order of error here, doesn't matter. You do a certain critical scaling, and then what you get is that you get a universal limit in the end. And this universal limit is precisely the multiplicative, so the multiplicative statistics of the direct two-point process, or it is precisely the Laplace transform of the KPZ solution. And in that case, if you interpret in terms of KPZ solution, essentially S over or minus S over T, and CV here is just a constant. This first variable here is the spatial variable or the spectral variable, the Laplace transform variable in your KPZ solution. And this T cube over constant is the time in your KPZ solution, right? So what you're seeing here is that for a large class of deformations of eigenvalues, you have universal limit where what survives is a certain spectral variable and the time variable in the KPZ equation, right? Which become universal. Yeah, so this is the result. Okay, I don't want to say much about here because I'm running all the time. But as I just briefly mentioned before that, that there's also, our techniques, they're based actually on this determinant structure, and there's a certain correlation kernel associated with this deformed statistics, those like multiplicative statistics. And this correlation kernel also has a limit, a non-trivial limit, which essentially is contracted out of this interdifferential Painlevé equation. Just to say that the statistics that we see in the limit, they correspond to a certain point process as well, which is constructed out of certain Schrodinger equation. Anyway, I don't want to mention more about that. The sort of a point process side of this of the limit of this multiplicative statistics. So you can also interpret convergence of point processes over there. Okay, finally, let me just wrap up. A lot of stuff, but let me just wrap up some main messages here. The main message that I wanted to convey to you is the following: that we were considering certain eigenvalues of random matrices and doing certain very general multiplicative statistics of them. And we proved a certain versatility result in the sense that this general family of statistics converge in the limit to a certain function, and this function coincides with the Laplace transform of the KPZ equation, narrow-eyed solution of the KPZ equation, and this function also coincides with a certain quantity of the area two-point process. And a way to sort of interpret those results, or a way to compute those limiting results, or the limiting objects in the results, is through this interdifferential Painlevé equation. And of course, we got this nice limit, this sort of limit that connects to various different things. But actually, the way we started work on this project, the way we actually considered first this multiplicative statistics for eigenvalues of random matrices is because it's because they appear also in the side of the KPZ solution. They are useful, and actually we were considering a certain discrete model. We're studying like the stochastic six-vertex model. And then we needed to understand sort of similar statistics but not for eigenvalues, but for other discrete models, and things were like nasty, extremely nasty. And then the natural sort of model, which things were simplifying a bit, was actually the random matrix model, and then we were allowed to consider then those multiplicative statistics for random matrices, not for the stochastic six-vertex model, and it turned out that they also had those nice limiting results. For another day, perhaps, but the point is that, and that was the point of my previous slide. Actually, although I focused today mostly about the limiting the multiplicative statistics of eigenvalues, but one could interpret those results of us in terms of point processes themselves. Not only we have convergence of these multiplicative statistics, but we can look at certain deformations of the original eigenvalues as point processes, as like a random process. And those deformations, they have to do with certain conditional thinning processes, and actually they have sort of our result then, the fact that we have a limit for those multiplicative statistics and that they connect their two-point process can be interpreted not only in terms of statistics, but in terms of convergence of point processes themselves. But I won't say much about that today. Let me just stop over here then. Thanks a lot.
Okay, so questions from the audience? So there is something that it passes me a little bit, is that of course in KPZ equation there is time.
Yes.
And here you are tempted to say that your eigenvalues are somehow evolving in time as well, but I don't understand. I don't know if there is such a type of interpretation.
You are absolutely right. The whole point is that when you are so there's not exact a time evolution, stochastic time evolution. So let me just look here this identity. So the point is that when you do this, so the identity that, I mean, the key identity here to connect, let's say, to the KPZ equation is this identity here, right? Mm-hmm. So you take essentially this Laplace transform of the narrow-edge solution, the KPZ, right? So KPZ depends on time, but you have certain state for the narrow-edge solution. You have a certain symmetry property. They can rescale time afterwards, right? And also take this expectation here. Your time now is no longer stochastic, in the sense that your time now is hidden in terms of sort of it's just like a parameter now, right? Just because of the way you rescale this h. You didn't write it down, but the way you scale this h is that you essentially do a certain scaling so that you see the height function of the origin, but we scale with t. So in a certain sense, this statistics here, so this connection here sort of happens at the level of a certain Laplace transform, and the connection, and if you look at it on the area side, your time parameter now is just really like a parameter of the area 2-point process. It's no longer stochastic. You lose the stochastic part of your time, right? And then what you do here is that when you try to recover this guy, when you try to use this kind of identity to recover the distribution of your KPZ equation, the type of result that you get is you look at your KPZ height, you rescale with time, and then the 1-point distribution of your KPZ, the 1-point distribution is a certain distribution which depends parametrically on time. It's just a parameter now. So this connection with KPZ point process, and therefore the connection with eigenvalues, has the KPZ time just as a parameter. You lose track of fluctuations, temporal fluctuations in the KPZ side, in a sense. Yeah. I don't know if I answer your question completely, Newton, but sort of, in other words, time now is just a parameter. So you cannot analyze time dynamics of eigenvalues in that sense. You don't have like a dynamical interpretation of time for us. Now time just becomes a parameter, really. Yeah.
Okay, but in a sense that it doesn't mean that it doesn't exist such an interpretation, time interpretation, right?
Yes. Okay. Yes. In that sense, it doesn't mean it doesn't exist. Yes. You just lose track of it.
Yeah.
Yeah.
Okay. Thank you. Okay. So if there are no more questions.
Or perhaps let me just add one thing, Milton.
Okay.
May be relevant here. Of course, we are looking at here not exactly as the stochastic evolution of KPZ, but the 1-point distribution of the KPZ, right?
Yeah.
And then if you look at this 1-point distribution, which is now a deterministic function, which depends on time, you can start wondering about let's say the interpretation of this time. But again, just it's not anymore like the stochastic dynamics, but just as a parameter. And you can actually one can prove, and actually I guess part of the things that we get here is that actually you can express this Laplace transform, which depends on time and on the spectral variable, directly in terms of a solution to MKDV. equation. And then time, we scale time in this rescale parameter, this rescale tempo parameter appears as a time parameter in the MKDV. In a certain sense, that's a reminiscent of this Matesky-Quastel-Remanic result, where they obtain a KP equation for the distribution of the KPZ fixed point. So in that sense, we do have some, let's say, some temporal evolution in time, some equation describing the time evolution, but it's not stochastic because we are now working at the level of the one-point distribution, not exactly at the level of the KPZ equation itself. Yeah.
Okay. Okay, thank you. Okay, so let's thank Guilherme again.
Yeah.
Thank you, Guilherme.
Thank you. Mm-hmm.